Welcome back to The Explainer. So let's just jump right in with a big question. What if our entire understanding of physics, everything we think we know, is basically like one of those ancient flat Earth maps? Brilliant for its time, but just completely wrong about what's really out there, over the horizon.
I mean, really think about that. For centuries, those flat maps were incredibly useful, right? They were masterpieces, but they were also incomplete. They worked perfectly if you were just sailing along the coast, but the second you aimed for the edge, well, the model fell apart. So what if our current map of physics is exactly the same? A brilliant tool that has served us well, but it's about to be replaced by a much more complete picture of, well, the globe. All right, let's start there. Because before we can even think about sailing beyond the map, we really need to understand the one we're using every single day. And it is a beautiful, incredibly successful, but ultimately incomplete map.
So on one side, you've got that old map. On the other, you have the standard model of physics. And let's be clear, this is arguably the most successful scientific theory in human history. It's the engine behind your phone, your GPS, modern medicine, everything. But just like that old map, it has edges. It has blind spots. It can't explain something like 95% of the known universe, all that stuff we call dark matter and dark energy. And if you look at the center of a black hole, the math just breaks. It literally goes to infinity, and we fall right off the edge of our own understanding.
Einstein himself got this perfectly. This quote right here really nails the dilemma we're in. Our models, our maps are incredibly powerful, but we can never ever mistake the map for the actual territory. The moment our math becomes perfectly certain and tidy, it stops describing messy, complicated reality. So if we know there's a whole world beyond the edge of our map, how in the world do we get there?
Well, what if the ship for that voyage, for that journey, is one single radical idea? This is where a fascinating new model called single point theory, or SPT for short, comes into play.
Okay, the core idea of SPT it's kind of breathtakingly simple. It says there is no pre-existing stage. There's no thing called space or time that stuff happens in. Instead, reality itself is being constructed, almost frame by frame, by a single point repeating a cycle over and over and over again. So everything we see, particles, forces, you, me, it's all just a really complex interference pattern, kind of like ripples on a pond, all generated by this one single fundamental process. And the speed of this frame rate, it's just staggering. I mean, look at that number. We're talking about 10 to the power of 43 cycles every single second. And this isn't just some number they pulled out of a hat. It's actually derived from fundamental physics. It's the time it takes a photon of light to travel the smallest possible distance we know of, the Planck length. This is, in theory, the universe's ultimate refresh rate.
So this leads to a really profound shift in how we think about things. In SPT, things aren't permanent, they are persistent. A particle, like an electron, isn't some tiny little ball. It's a stable, self-reinforcing wave, a kind of resonant knot in the fabric of all that interference, a knot that just lasts long enough for us to point at it and call it matter.
But, okay, that's the big question, right? How does a fleeting little wave become a persistent particle, a thing? For that, well, you need a new kind of math. You need a new navigational chart.
Okay, don't let the symbols freak you out. I know it looks intense. Most of this equation just describes a simple wave moving through space. The real magic, the secret sauce, is in that last little part, the feedback term. Think of it like this. If you stir some water, you get a ripple, and that ripple just fades away, right? But what if? What if the ripple's own energy could somehow grab the water around it and keep the stir going all by itself? That's what this term does. It is a mathematical feedback loop that allows a wave to sustain itself. It turns a temporary ripple into a stable, persistent whirlpool.
So you can think of it as this four-stage process, going from pure energy to actual existence. A faint wave starts to move through the field. But once its intensity hits a certain sweet spot, that feedback loop we just talked about kicks in. It starts to feed on itself, to self-reinforce, it gets stable, and then, boom, a persistent, localized knot of energy emerges from the field. And that is what we perceive as a solid particle. It isn't put there, it literally builds itself.
And this whole idea of persistence, of building yourself out of the field, it leads us directly to one of the biggest mysteries in all of physics. Where does mass even come from?
In single-point theory, mass isn't something a particle has. Mass is something a particle is. It's a direct measurement of the intensity of that self-reinforcing wave interference. The more intense and tightly packed that little wave knot is, the more mass it has. So mass isn't some label you just stick on a particle. It's an emergent property of the wave's own geometry. And this right here is a huge, huge shift. The standard model, our current map, it forces us to go out and measure the mass of every single particle. And then we have to plug those, 19 plus different numbers into the equations by hand. They're just arbitrary. SPT, on the other hand, says, nope, it suggests there's only one fundamental constant for this, that beta value. And from that single constant and the shape of the wave, you should be able to calculate the mass of every single particle.
So that leads us to the ultimate test, right? This is the moment of truth. If your new map of the world is better, it has to do more than just get you home. It has to successfully navigate you to a known destination that you've never been to before. For SPT, that destination was predicting the mass of the Higgs boson. And the logic they used is it's beautiful. It's so clean. First, you calibrate your machine. You take a particle you know everything about, like the proton. You use its known mass and wave shape to calculate that one universal constant, beta. Step 2, you run a simulation. You smash two of these proton waves together at high energy, and you see the exact shape of the new particle that forms from the wreckage. And then, finally, the moment of truth. You take that universal constant you got from the proton and you apply it to this brand new shape. The equation then spits out a prediction for the new particle's mass completely from scratch. And the prediction that came out of single-point theory for the mass of this new particle was 125.3 GeV. That stands for giga-electron volts. It's just a standard unit of mass for these tiny particles. And the actual measured mass of the Higgs boson that they discovered at the Large Hadron Collider in the real world, 125.25 GeV. The agreement is just stunning. And the crucial point here is that this wasn't a guess. This wasn't fitting the theory to the data after they already knew the answer. It was a genuine, bona fide prediction deriving the mass of one particle from the properties of a completely different one, all linked by a single underlying principle. But look, finding one new continent isn't enough to prove the world is round. A really powerful theory can't be a one-trick pony. It has to do more than just explain what we already know. It has to guide us to things we don't know. It has to make other new predictions that we can actually go out into the world and test. And SPT does exactly that. It predicts that because of that universal frame rate, light from really distant cosmic explosions might actually arrive at slightly different times depending on its energy. It predicts whole new families of undiscovered particles, those self-sustaining wave knots it calls solitons that should show up at even higher energies in our colliders. It even offers a natural candidate for dark matter, weakly persistent waves that have mass, and therefore gravity, but just don't interact with light. And these aren't just vague ideas. They are concrete, specific, falsifiable predictions. We can build experiments to see if they're right or wrong. Which, brings us all the way back to where we started. Single-point theory offers this incredibly compelling, elegant, and testable new map of reality, all derived from one single idea. It wants to replace this messy zoo of particles with the simple harmony of interference. But is it the final globe, the true picture of reality, or is it just a much, much better map whose own edges we just haven't discovered yet? I guess only time and a lot more data will tell.